I'm gonna need some volunteers. Uh, Pavel, okay, come on up. So you guys are going to be come right here. Gonna wait. Could also get another volunteer. Could be four. All right, there we go. So what we're gonna do right now. Oh, are you coming? So this is a live demo, so this could go really badly, especially because I can't really control what's going to happen right now. So, so what we're going to be doing is we're going to be showing a version of how one can do things in real time, and then we're going to see what happens. So, if you guys could just stand there. I was going to have oh, there we go. So it's going to, this is much harder than I thought. Wait, there we go. And so it's gonna do. Can you guys get closer? Because it's doing right now. We're gonna discuss this. But what's happening right now is the computer, the camera feed is being turned into edges are being processed, and then those edges are being used to guide the diffusion process. And so what I'm gonna do now is if I can like find my mouse, where's my mouse go? Oh, there. There. Oh, no. There. Okay, so that's one image. Then we're going to change the prompt. Stay right there, because it's easier for me to just do it this way. And now we're going to do pirates. And that's going to change in real time as well. And then now, oh. Live demo land. And then, now we have pirates. And where is that mouse? And wait, can you guys get closer again this time? I don't buy it, I promise. Come on closer, come closer. It just makes it easier for me. Because this is some. And all right, not all of you are gonna be picked. And wait, there we go. Oh my God, this is so trippy. Okay, well, now you guys can go take a seat, and then you will receive a photo print of this. Even though it's going to be very crappy. So I'm going to go select the photos that I took. This one, so right now it's lower resolution, but that's okay. That's because it speeds up the process. Then we're going to grab the original one, and then we're going to also pick one of the crappy pirate movie pictures that I took. So I apologize that it's so crappy. Which one? I guess we'll do this one. Where not everybody's in the frame. Then we're gonna do generate strip up. And we're gonna select the printer. And now you will have something to remember this moment by. I wish it could have been better. I had a camera, but the camera stopped working, so I had to use the webcam. It would have been easier if I just had the camera just pointing at people. But anyways, all right. Now we can go back to the slides. Okay, so what you just saw was not super real time, but it was pretty good. I mean, that was on the laptop. And these are GIFs showing like the sort of differences. Obviously, the quality is a little bit degraded because they're GIFs or GIFs, however you want to call them. But on the right side, we have an RTX 4090. And then on the left side, we have a MacBook M2 Pro. And then you can see that I'm changing those prompts in real time, and it changes pretty quickly. The difference in speed is actually quite high, but it's not too bad. And also take into account that this is using a Gradio app backend, which means that the HTML page needs to be refreshed. So it's never going to be super real time, but it's pretty close. And in what we're going to do today, we're going to do one that doesn't require doing Gradio, but I will also have the Gradio code up. So actually, this is a QR code generated with also one of these models, one of the ones that we actually are using here. It's called ControlNet. You can scan the QR code because we do need to install a lot of models and they take up a lot of space. You don't need to whip out your laptop and work along because you're going to have to wait to download the models before you can play around with it. But you can use this to save for later. It might be private right now, but I'll make it public. So a little bit about me. I'm a neuroscientist. I study brains. I like to study brains by looking at how our understanding of space changes. So, say for example, we are in this context. How does being in this context with all these people, and if you're not from Lithuania, being in Lithuania, how does that influence the way that you remember? And there are things about our brains that use sort of pieces of prior knowledge, frameworks of prior knowledge to sort of help us predict. And so I use augmented reality and virtual reality, and fMRI and EEG, and I'm trying to combine all of those together to understand the process better and essentially read people's minds, but not in an evil way. Then the filmmaker part of me, it's like something that I do on the side. I like making films. I make them about the ethics of AI, about tutorials, things like this. Interestingly enough, I think a lot of how I think about editing and the whole artistic process of creating a narrative or a story has really influenced the way that I study the brain as well. And then lastly, I'm a bit of a futurist. I organize conference on the future of AI, ethics, virtual reality, augmented reality. And with that comes an entrepreneurial side of me. So if you're also an entrepreneur-ish and you're also like a full stack developer or something like that, and you're interested in like, maybe like ideating together, let's talk. And also if you're interested in learning more about ethics or that's a topic that's you're passionate about, the ethics of the future, also please reach out. We're going to go through basically a couple of stages. The first one's the landscape, what's available out there to do these generative images. We're going to go through a little bit of the closed loop, the closed source, and the open source. We're also going to go through the basics of how diffusion models work. They're quite complicated, but overall, despite the huge advances that have happened over so many years, well, not so many years, maybe like 3 years, they are not super difficult to understand once you get the basics. Then we're going to talk about what makes us able to do this in real time, because I don't know if you've ever tried some of these models in the past, even the ones that were on the web, they took a long time to generate an image. So how was I able to have that camera feed and like generate something so quickly, even though it's just a laptop? And then we're going to go through the implementation. And if you're interested, and if there is time, I made an AI movie with a mixture of these methods. It's about 2 minutes. I'm probably going to run out of time, but we can either do that or questions. You guys will vote at the end. Okay, so there's you've probably heard of these products, DALL-E, Midjourney. Who here has used Midjourney or DALL-E? Okay, which is your favorite? Midjourney. DALL-E. Okay, yeah. So these are the sort of closed source products. They're at the beginning. There's papers that come out that do describe the process, but they do tinker and then do make modifications on these models to make them a little bit more special, so that people will pay for them. And then there's many, many more of these types of products. Oftentimes, they're just wrappers over Stable Diffusion. And you'll be able to make your own wrapper as we'll go through today. Then there's the open source world, Stable Diffusion, Flux, Kandinsky, and many more. But all of these, they all share something quite similar. They might have slightly different architectures, but they all are about a diffusion model. They all have that. They just tinker with it and have a different set of architectures, but the principle remains the same. They are diffusion models. And more recently, latent diffusion models, but we'll get into that. So most of us are coders. We love to sit on the computer, not on it, with it, laugh with it. The computer is our friend to some extent. And so we like to type and script. So we're going to be talking about scripting, but scripting is actually not the most popular way of using these models. They're actually just wrappers that people love to use. And the most popular one is Conf UI. It used to not be the most popular one, but it became the most popular one. So I thought it might be interesting if you're interested in not doing this in a form that requires coding or anything like that, you just want to play around with it, these are really good alternatives. So I thought I'd talk about them. So Conf UI is mostly a node-based program. You have nodes. You might have say this is a prompt node, and then you connect that prompt node to your model node, and then you generate something. Some other people made these, and you can also make your own node groups, and it's actually a really cool community that has been rapidly developing. This is the most flexible of all the different systems, more flexible than Midjourney, more flexible than anything else. You can do so many things in Conf UI. And as you can see, the node structure can get a little bit complicated. And this is not even as crazy as it gets. If anybody's played with Blender and used shader nodes or geometry nodes, you know it can be wild. Automatic 111 was also a very popular one. It was the most popular one because it was also one of the easiest to understand. It looks kind of similar to the demo that I showed you. They're using the same backend, Gradio. And although it's not as popular anymore, it still has tons of plugins that make it really easy to use, and you can just go to the GitHub, and it's quite easy. Now, Touch Designer. This is a more recent one. I don't know if, we have someone that loves Touch Designer. It's mostly used for music visualization. It's a really amazing piece of software. If you've ever gone to a music show, you might have seen all these really cool visualizations. Oftentimes, it's done with Touch Designer. There's other ones like Max MSP and some other ones, but this one's a very popular one. And it's also node-based, and there are plugins now where you can use Stable Diffusion to do things in real time as well. So we can't really go into diffusion models without talking a little bit about deep learning. So deep learning is basically just a neural network that has more than just 2 layers. That's really it. It's deep doesn't mean it has to have tons and tons and tons and tons of layers. So the basic idea is you have some input, and then you follow an order of matrix multiplications that are sort of biased with weights. And you go through a sequence, and that sequence is just determined by the layers that you have. And in this example, this is a feed-forward neural network. You have some outputs, and you have inputs. Very much like regression, you use those inputs to predict an output. The only difference is that the learning is a little bit more black box. And it's black box because as you say, like say for example, you have cholesterol level, age, and you're trying to predict if someone has heart disease. You give the model input. You know what the truth is. You know that the chest pain, the resting blood pressure, the cholesterol level of this particular patient, they have heart disease. The model doesn't know that. You give it the inputs. It predicts what this person has. It doesn't predict heart disease. Then you say, hey, you were wrong. They do have heart disease. So then you do a difference between the prediction and the ground truth, and then you tell the weights to update to try to be better at making that prediction. And you do that iteratively over time until the weights become organized in such a way that they are able to predict heart disease well. At that point, you have stopped training, and then you freeze the model, and now you can use it in production. And there's many different architectures that are good for different types of things. So the one that I just showed you is a feed-forward neural network. We have convolutional neural networks. Those are really great. Usually, if you want to do something with images, you want to keep the spatial relationships between like the features in this image. So if the tree is next to the dog, that's kind of important, right? Especially if you want to do sort of image recognition and things like that. If you were using a feed-forward neural network, you'd have to take a 512 by 512 image and flatten it into a single vector and then feed that in. But then you lose a lot of that spatial information that's really important that describes really important things about that image. And then you have other types of neural networks as well. Each of these architectures helps inform and helps you with different tasks. So I think I love this quote. I'm not even sure if Michelangelo actually said this. I couldn't really find if there's a document where he says this, but I also didn't look that hard. But I like the quote anyways. Every block of stone has a statue inside it, and it's the task of the sculptor to discover it. I think this is a very apt way to describe how diffusion models work. And I'll describe that in a second. So at its simplest form, think about noise. Let's just say a noisy image, kind of like a block of stone, in that quote. And then the diffusion process, the reverse diffusion process as it's actually called, is you start subtracting noise little by little by little by little by little until you reveal an image, kind of like sculpting a statue that's already in the stone. That's the reverse diffusion process. But we actually start training the model through what's called forward diffusion. So in order for the model to understand how much noise to remove from an image, even though it's just pure noise, it needs to learn what noise is. So you have to teach it different levels of noise across time, and then it learns a mapping of how much noise between every time step. So when you're making inference steps, when you see inference 1, inference 2, inference 3, inference 4, that's going through a schedule of noise reduction. And it was used also in the training for noise addition. The main ingredients of Stable Diffusion, it's not really just one model, it's actually 3 models. So when we think of Stable Diffusion, when we talk about these models, we often think about them as the model. But oftentimes, the models that we see in papers, when they're being developed in some way, they're actually a sort of conglomeration of a bunch of little models, sometimes really big models. In this case, these are 3 really big models. We have the text embedding generator. I like to call it that way because that's really what they're using it for, called CLIP. Then we have the variational autoencoder, the VAE. This is the compressor-decompressor, and I really love this one. I think it's a really cool concept. And then the unit, the most important part to Stable Diffusion, and that's the noise predictor. So I talked about that noise. We'll get into that very soon. So let's go into CLIP. So CLIP is a very interesting concept. So you have the whole point of clip is to try to make, if you have text and you want to turn it into numbers, because then you want the numbers to be computed by a network, you need them. How do you make sure that they somehow align to an image? Well, the whole idea of clip is we have a database of images, and all those images have captions. So we have a text component to an image, and we also have the actual image. So clip's whole idea is like, I'm going to generate some vector from an image. I'm also going to generate some vector from the caption. And then I'm going to try to make them as similar as possible. The similar they are means that if I just took a caption, I could then generate an image. If I just had an image, I could generate a caption. That's the main idea. Interestingly enough, in Stable Diffusion, the only thing that's really used is the upper part, the text embedding part. And within the unit, you actually end up learning the semantic similarities between the text embedding and the image. So they don't need to do it at this point. They just use it to have a good starting point for creating the vector from a caption. The VAE is better thought of as two smaller models, the compressor and the decompressor. And the basic idea is you have an image, it's in pixel space, and you use a compressor to basically downscale that image into some super low resolution pixelated image. It's not really in pixel space anymore because the neural network does transformations on it that actually start retrieving semantic information within that image. So they call this the latent space, and so this is a latent image. And then you can use the upscaler, the decompressor, to bring it back to its normal original form with some loss, but almost imperceptible. And if you do a difference between the images, it's actually pretty impressive how much you can compress these things. So, okay, compressor. Okay, does that mean that if I have this crappy resolution image and I don't want to use up my Google Drive space and I want to send you this image, but I want you to see the full image, how do I do that? Well, we both have to have the same VAE. So if I have a VAE and I compress it, and now I have this tiny image, and then because I don't want to use up my Google Drive space, I don't want to start paying for that. And then I send it to you. You have that same VAE. You can decompress it back to its original form. So that's one way to actually do transfer of information at low size. Is everybody following so far? Great, great. So why do we want to do this? Why does Stable Diffusion care about this? Why not just do all the transformations in pixel space? Well, it's because it's very expensive. If you have an image like this, that's a lot of pixels to deal with. When you do things in a smaller amount of resolution, smaller size, smaller everything, doing computations in this world makes things more efficient. And then when you're done doing the things that you need to do, then you just use the decompressor to bring it back into its normal size. It's really just a computational efficiency issue, and it actually ends up having really cool properties. Okay, the unit. The whole idea behind the unit is to predict noise. If I give it this latent noisy image, and from now on, by the way, when we're talking about images, we're really talking about the world in this space, in latent image space. So if I use latent, that just means that we're in the compressed form. So the unit, the whole idea is that it takes many different types of inputs. One of them can be a text embedding, another one can be a noise. And in this process, it actually learns to map semantic similarity between the text embedding that your caption and the noise an image with noise, without noise. And its whole job is to tell you how much noise was in this image. Right now, this is just a pure noise, and that's also pure noise, but it is different noise. But yeah, so that's basically the whole point of the unit, is to predict noise, and this will come in handy when I describe this graphic. Okay, so let's go through it. I know it's a little complicated, but I will not do any math, so we're okay. We're okay. Okay, so this is during training. This is how Stable Diffusion learns things. So at the beginning, we have a giant database, a giant database. A lot of these models use the same ones, but now some of them use extra things, and obviously some of them hide the things that they use the training on because they're afraid of copyright infringement issues. Midjourney had a couple of these things where some of the images that were revealed were not supposed to be there. That's why they can do such great art from like specific artists. But this is the case from all models, unfortunately. And again, these ethical issues, these are things that I care about. If you want to talk about it, we could talk for hours. So the database starts with a bunch of images, and they have a bunch of captions. As I remembered, clip, that's the text encoder, the text embedding generator, remember? So we take that caption, and that turns into a vector. We take our image, we send it through the compressor, and then we get that latent, lower resolution image. What we then do is that we add a little bit of noise. We know how much noise we added because we chose how much noise. And then we take that image plus the noise and the text embedding. And then we ask the unit, tell me how much noise there was. It makes a prediction. I know the ground truth. I know how much noise I added. And then I ask it, hey, that was not great. We take the difference of that, and then we update the unit weights so that it gets better at predicting noise. I do this at different noise levels. That means that I know when I add a lot of noise, the image should be really crappy. You should predict a lot of noise, because that's how much noise we have to remove. If I added a little bit of noise, you should remove a little bit of noise. And so the unit over time learns to predict noise at different levels of a latent of a latent image with some noise. And it turns out that you think, oh, you can just go from, okay, if it learns to predict a lot of noise, why can't we just predict that and do inference really quickly? Unfortunately, it doesn't work like that as easily. Although one of the models that we're going to talk about uses, well, we'll get into that. You're right that that is possible, but this process, there's been many methods that have tried to optimize it. This process does need to be iterative, because you're navigating probability space, and if you take a big step, you might overstep the local minima. And so you need to make sure that you're going in little steps. So you go through a probability flow that leads you to an image. It's a little bit more complicated than that, but that's why we have to do things iteratively and not make big steps. So now this is inference. Our model is trained. It knows how to predict noise. So now we don't need an image. We just send it some prompt. We turn that prompt into a text embedding. So now it's in vector form, understandable by a computer. And then now we start with some noise, just some random noise. We give it the text embedding, and then now the text embedding is helping us guide the process by removing noise towards a space that contains a cat in a sunny field. Once we've reached a certain point of denoising steps, now we can use that decompressor to bring that image back into a resolution that we like. Okay, so this is text to image though, but you've probably seen that you can also use images as references. How does that happen? How do you use a reference image? This is just trained for text embedding, so what's going to go? Oh, wow. We just use that noisy image and use a reference for that instead. So now we have a text, or some prompt. We turn it into a vector, but now we have some reference image. We compress it, turn it into that latent space, and now we add some noise. And now, instead of the unit starting with just pure noise, we give it some noise that has some structure. And then from there, it starts predicting noise and using the original reference image to build something new. And that's how image to image works. So there are many types of plugins that one can use in Stable Diffusion. So it's such a big model. Has so many different components. You can start imagining that you can start hacking some of those components. And so one such type of hack is actually called the ControlNet. And the ControlNet is basically a hypernetwork. It makes a copy of Stable Diffusion, a section of it, and then it does the training on that section. Now that seems really a great idea, because instead of having to train the whole model again, you just train a smaller aspect of it. And then you can make modifications to that. So one cool use of this type of training is now you can use different image databases that are not in the original image set to train it to learn how to do things that are different. So, for example, what if we have a database full of depth maps and we want to be able to use the depth maps to inform the inference process? Say you're a 3D modeler, and that's a great way for you to have your depth maps turn into something. What if it's normal maps or poses? We want to have control over how things move in something in real time or in video. These are all different types of image types that are not usually in that are not usually in the databases, and that's pretty cool. So now we have different image types that we can use in the guiding process. Obviously, these all take different. They might require different pre-processing steps to extract the poses, but that means that a Stable Diffusion model can use these formats to generate something. And today we're going to be going through candy edges because that one's really quick and it gets the job done. So how would ControlNet inference work? So just like we described, we have some prompt. Then we use clip to convert that into a text embedding, and then we send it into the unit because we're going to want to predict noise soon. We have an image. We do some processing, the edge detection in this case. We get a version of the image that's through edges. It's called canny edge detection. There was a guy called Canny. He developed an algorithm to detect edges in images. Then we compress it, and then we send it to the ControlNet, which is now part of the unit, and then we do the inference process through there until we generate our image. And diffusion is really, really powerful. These are just 3 examples, but it's really great at image reconstruction without inventing new features. It actually can recover features from like MRI data that's not really great. It's very powerful and could be really useful in the medical community when you have bad quality MRIs, but you still need to be able to read something about them to help people. Then you can also do music generation with it. So think about this. A spectrogram, right, frequency and time, that's kind of like an image. It contains our frequency information, and it goes over time. Well, you can train models with music by turning the spectrograms into images and then following the diffusion process here. And this is from a hobby project from someone that used spectrograms to develop it. And like the music that comes out of it is actually not so bad. And then more recently, we have video game simulation, which is just crazy. I cannot understate the wildness of what this actually means, of simulating. What you're seeing right now is every frame is being generated in real time, and it's never been a frame that has existed before. And someone can play Minecraft in real time through diffusion. There's no physics, there's no physics engines, there's no pre-coded things. This is just generating a frame, a playable frame. And that's diffusion is powerful. So what makes these generative processes fast? Well, you can kind of guess at some of like the ways that you can do this in real time. Obviously, if you have a GPU, you'll be okay. You'll be okay. If you don't have a GPU, then hopefully you have a laptop that does, or you have maybe a Mac that has their software MPS that sort of optimizes the Mac GPU. CPU, you can still generate things. It's just going to be much, much slower. Also, floating point precision. So let's say, think about these as terms of decimal points. Let's say that you have a text embedding, like the ones that I talked about, and there's like 7 decimal points, and you're doing matrix multiplications on these things. And you have to now consider 7 decimal points every time. That's a lot of space and memory. So instead, we can use half precision, use less decimal points, or even less. And now it's possible to use 8-bit precision. And you can imagine how that will speed things up because there's less things being loaded up into memory. You can do architectural changes, like instead of having a really big compressor, decompressor, you make it really, really small. And so that might sacrifice quality, but at the same time, you gain speed. You can also have algorithmic hacks, like loading more things into cache, preloading models, accelerating tools. You can have a plugin selection. As I mentioned, pose detection can take a bit, depth detection can take a bit as well, but canny edge detection is super, super fast. So that your selection of how you're going to process an image is also very important. And then there's also the most important one, in my opinion, which is distillation. So all these models, some big company trained them. They spent millions of dollars doing this, and they did all the hard work. So we should use the model that they allowed the world to use that's open source. Instead, what we do is we have a teacher model, the pre-trained model, and then we have a student model, a much smaller model that learns what the teacher model has. And so now you can have a much smaller model that you don't have to train from the ground up. You use a teacher model to teach it. What do you want it to know? And so how exactly would this work, for example? So say, for example, latent consistency models, LCMs. You might have seen them as plugins if you played around with these things. So we have our image. We're doing the training, right? We have an image. There's no noise, but we're going to do a noise schedule to start adding noise so that the unit eventually learns how to predict noise properly. Well, an LCM, basically, at its core, what it does, it say, OK, hey, teacher model, where are we right now? And it says, like, oh, we're over here. We're at this step. And then the LCM will say, OK, I'm just going to try to predict the original image from here. Don't just stop what you're doing. I want to predict. And then it's going to go through another training step. And it's going to, hey, teacher model, where are we now? Oh, we're over here. We've added a lot of noise. It's like, OK, I'm going to try to predict the original image. And so basically, this is the main idea behind LCMs. And this actually works really well. So you go from like 20 to 40, from 50 inference steps to just down to 2 or 4. And what you saw in that demo, that was an LCM. So the implementation is really simple. That's it. That's it. Thank you, everyone. I'm just kidding. So what's beautiful about this and why it's so simple is because Hugging Face, they have this diffusers library, and they're a really, really great open source community. You can contribute if you want to. And they basically allowed this Python library that does all the heavy lifting of loading up the models, loading up the weights, and it allows for a lot of flexibility. We're going to go into a little bit more detail than just that code implementation, but the general idea, just so we are all on the same page, because I'm going to start showing some code now, is we have some prompt, as you saw in the demo. We have an input image, and we have to process it. As you remember, that's like edge detection. And we wanted to use edge detection because we want, when we create an image, we want it to follow the structure of what's happening if we want to do real time, as you saw, where we have like a person and we want them to take a certain shape. If we don't do this, then we're not really guiding the structure of the image. So we want some sort of thing to process it. In general, though, if you're just doing text to image, you don't need any of this. But I like doing this real time, structure of an image. So we process it, and then we have the generative model that takes the processed image, and then it outputs the generated image that took the processed image as an influence. So in other words, we have a camera feed, we have edge detection, we have the optimized model for fast generation, and then we have the generated image. So the diffuser syntax is quite simple, and I just love how beautiful everything ends up being. We have the pipeline class. And this class is incredibly powerful. This is really what's handling the heavy lifting for almost everything. We have very simple methods that we can use to call a model and load it into cache. And then we have a way to call the pipeline with prompts and other arguments. And I'm going to go through those in a second. So this is a very simple function that does the canny edge detection. You can see that I can use OpenCV, if anybody's familiar with OpenCV. Yeah. You can really easily just import OpenCV. This happens super, super fast. And then all you do is do the image detection, the edge detection, and then you have a new input that you can then send into the model. The generative model process is, well, as I said, we're using a ControlNet, so we need more than just a base Stable Diffusion model. We need that ControlNet. So we use a ControlNet model class, which also comes from diffusers, and then we load up that model. We give it its location. We specify the torch type, which basically is whether you want to do mixed precision or not. So that's one of those hacks that I was telling you about, whether we want to do 32 floating point numbers, 16 floating point numbers. We want to use 16. It speeds things up significantly. And then we create our pipeline class, also loading up that model. We tell it what ControlNet we want. And I have the safety checker to none here. It protects for NSFW stuff. But there's a lot of false positives, so sometimes it just ends up with black images. So I set that to none. And then we have a function that calls the pipeline. 10 minutes? OK. Oh, wow, great. We might have time for questions. I'm going a little faster than I thought then. So then let's get through this real quickly. So once we have the pipeline class set up, we have a bunch of parameters that we can set it to. We have the prompt, the number of inference steps, the width and height of the image that we want to generate. And then, of course, we need to refer to our edge-detected image. So this is that after going through that canny function, that's where we send it. And then we have other parameters for the ControlNet, and then we can return the generated image. It's as simple as that. And so now I thought that it's going to be a little bit difficult because this is it's harder to do this because it's slow. But let's give it a shot. Oh, wow. So now I'm going to do okay, so I thought it would be useful for you to just see it in action. So this is a very simple script that I made. I also have the Gradio app that's on the GitHub that you will have access to, which is I try to keep things separate so it's not super optimized for efficiency. I kept it in a certain structure so it would be very obvious how the loading of the models works and everything like that. So we load our libraries. Over here, it's just a very simple utility function. All it's doing is it's checking your computer and finding out whether you have a GPU or not. And then if it does, then it sets everything up so that in the future, you use the GPU to accelerate things. Then you can you have these global variables. As I said, you choose you have to make sure that you choose the model location. Right now, ideally, you would have it within the computer and you have it in a upstream models folder. But these models take up a lot of space, so oftentimes I kind of just this one particularly is on my machine, but I usually have an external hard drive where I like put those because they took up so much space. And then over here, you can ignore most of this. That's just to create a consistent seed because you want the generation process to be a little bit more consistent, so you want to choose the same seed every time. But this is just another utility function that just grabs a cutout of the camera feed to make sure that we have something that's in the resolution that the model can handle, because they are trained at certain resolutions. Newer models are trained at a higher variety of resolutions, but they're usually trained at the particular resolution. So you have to make sure that you don't give it something that's not that, because then it won't know how to deal with the pixels. And then, as I said, we have that process edges function. Now it's called something different, but that's just a canny edge detection. And then, as I said before, we have to prepare our classes. We prepare the ControlNet model and the pipeline class, and then we return that pipeline. And then in this function, this is just what we saw earlier. Now we use the pipeline class. And over here in the run model, you can see how I'm setting these up. This is for readability. You can make it more optimized. And then OpenCV allows you to do a video webcam capture. And so this is just a few lines to say, hey, read the camera feed. And the while is like, say, keep doing this for every frame. And then over here, this is where the magic happens. We just have, we grab a cutout of the camera feed. We process it to do edge detection. Then we convert it into a file type that the model's like, which is a pill image, not a NumPy image. And then we run the model. And then we, over there, that's the received image, the generated image, and then we just put it in the center of the screen. And as an example, I am going to show you what this ends up being. And I'm going to move it over here. So that's also happening in real time. So that's me. It's a little slower than usual, because I think that this HDMI is much slower. But yeah, so that is the... this is also going to be in the GitHub, because I think that this is a more digestible version than the Gradio app that I made. Now I'm going to slowly start removing these things if I can. Oh, wrong way. And then we go back to the slides. Oh my God, where is the mouse? Oh, there. Where did it go? Does anybody see it? Oh, there. There. Okay. This is a struggle bus. 5 minutes? Okay, great. So the QR code that you saw at the beginning was also generated with a ControlNet. Now, as I said, ControlNets can be trained to take particular image inputs. So there are people out there that decided to make a ControlNet for QR codes, and they work really well. You could also use candy edge detection to create a QR code, but these work better. Although the candy one, the edge detection, actually is pretty good too. And I obviously chose hot air balloons because Vilnius, I don't know if anybody caught that, hopefully. And yeah, so like what you saw today is a sort of like an accumulation of many different tools and different ways to think about AI, things that you can do at home. And my brothers and I, we were in the process of finishing up a book that goes into deep fakes, facial recognition, music generation, so that you can do this at home. For me, there's a very huge value of being able to have things locally on your computer and not rely on servers, because then you can like tinker and play around more easily. And that'll be available in the spring. So if you're interested, we can talk. And then, so here's the part that I wanted to ask you guys, because we only have 5 minutes. Do you guys want to see a short AI movie? It's 2 minutes, or go into questions, or go into questions first, and then see the movie, or movie first, and then questions? Movie, okay. So okay, let me see. There we go.
Tell me what you saw.
They are not like us, Derek.
It's not supposed to be
This
something.
map was entrusted by our ancestors, and for generations we swore to protect it.
They are not like us.
Now, what did you see?
I see you in many places, many times, many faces.
It seems no matter what we do, we always end up in better.
Try to keep up this time.
I don't know who they are, where they come from. But I do know who we are, and where we come from!
That was Blender, this last part. But everything else was AI, except the voices too. I use real voice actors. But yeah, if you have questions about how I did that, we can talk about it too. But yeah, thank you for your time.